Welcome everyone to this conference, Canada, Mexico, USA, Algebra Conference, whatever it's called. It's a very long title and many organizers. Welcome. Okay, just one note, we'll have our conference photo will be held today at 12:30. So at the end of the morning session today. And without further ado, our first speaker is Vyjayanthi Chari from UC Riverside. He'll speak on higher rank KR modules, monoidal categorification, and imaginary modules.
Thank you. Thank you for the invitation to speak here. I'm very happy to be here. It's always nice to be in Montreal. So I'm going to talk about some recent work with Matheus Brito. But before I do that, I'm going to spend a lot of time telling you how all these subjects that we're talking about are related, namely quantum affine algebras, the representation theory of GL and F over a local, where F is a local non-archimedean field, and cluster algebras. So the connection between quantum affine algebras and the representations of GLN actually has been known for a long time because it comes through a Schur-Weyl duality, which goes from the representation theory of AN, quantum affine AN, and affine Hecke algebras. And this actually was proved independently by me and Presley and Ginsberg, Kapranov, and Vassereau in 96 and 97. But somehow it never really got exploited. I mean, everybody knew it was there, but there wasn't so much interaction between the subjects, and nobody actually saw what was going on. And that really continued until more or less 2015, when Hernandez and Leclerc developed their theory of monoidal categorification of cluster algebras. And then it began to be more obvious that there were connections, that people were studying similar questions. So I want to explain these similarities and how the subject developed before I sort of start talking about the newer material. Okay, so we don't need to know anything about quantum affine algebras. We need to know that it's a Hopf algebra, and that it once you have a Hopf algebra, when you're studying its finite dimensional representations, then it's automatically a tensor category. So it's a nice rigid tensor category. And so you can talk about its growth and decay. Okay, and the growth and decay has obviously basis of irreducible finite dimensional modules. Okay, and then the question is, what is this basis indexed by? And traditionally, one used to say that they're indexed by Drinfeld polynomials. Okay, so by an n-tuple of Drinfeld polynomials, so where n is the rank of the algebra you're considering. Okay, so it's actually much easier to think of this, in fact, as a monoid on infinitely many generators. So you have one for let's see, you have one for every integer between 1 and n, and one for every non-zero complex number. So it's an absolutely huge indexing set. So let's see what happens in the case of GL and F. Here it's known that that the representations, they have some conditions that the representations have to be sufficiently nice, but it's known that they are indexed by what are called the Zelevinsky multisets. Okay? And so multi-segments. And what is a multi-segment? It's just a collection of intervals, I1J1 up to IRJR, where you require that the IS and JS are integers, and S varies from 1 to R. Okay. Now, each of these, so if you take a single interval, it determines for you a one-dimensional representation of the corresponding GL, J minus I plus 1. And then what is the irreducible module? You take a parabolic induction, and then you get a module for GLN, for the appropriate GLN. And that module contains a unique irreducible submodule, which is the SOCO. So that is the irreducible representation associated to these multi-segments. Yeah. Okay. And so in the literature, they also work with the monoid given by these multi-segments. Okay. And then, as I found out recently, it's actually the two monoids are exactly the same. There's a one-to-one correspondence between multi-segments and these Drinfeld polynomials. You have to impose this restriction. So you need an integrality condition. The multi-segments came with integers as their endpoints, so you need an integrality condition. And so what is the connection between the two things? So we're now going to work with the parameter a being only over the integers, and you have this parity condition that you need to put in. But once you do that, you have a morphism of monoids, which takes the Drinfeld polynomial omega IA and maps it to that single segment. Okay? And it's actually very convenient to work with these multi-segments. I mean, I've worked, for 30 years, I've worked with Drinfeld polynomials, but I've realized really it's better to work with multi-segments. Many things just appear much more natural in this language. Okay? So for instance, I want to give you an example of that. So as I said, these Drinfeld polynomials index representations. The representations associated with the generator, omega IA, is called fundamental. Okay? Now, if you take a standard question in this theory is, when is the tensor product of two representations reducible, and what are the points of reducibility? What is the dependence on A and B? Okay, so if you take the tensor product of two representations, fundamental representations, it's known that the condition for reducibility is given in this way. So the difference of the parameters, B minus A, must be equal to I plus J minus 2P. So it's a bit like a Clebsch-Gordon rule, okay? Which is always a bit annoying to remember and very annoying to work with. Okay? But if you do it in the language of segments, it's absolutely beautiful. All it means is, so you translate omega IA to the interval I1, J1, omega IB to the interval I2, J2, and all you want is that the intervals overlap. So it's sort of completely transparent what happens in this language, and doesn't require, and it's really natural. Okay? And then the other thing that you always want to know is, what is a Jordan-Holder series when the tensor product representation is reducible? Right? So if you look at the literature, it's very unpleasant to write it down. It depends on which index is bigger and which parameter is bigger. But in the language of intervals, it's totally trivial. The irreducible head is omega I1 J1, just the irreducible module associated to the product. And the irreducible kernel is just obtained by changing the endpoints. So you have these overlapping intervals, right? And you make them non-overlapping. So your intervals are these, and you require something like this, and now you just do this. And yeah.
What is this product again?
You're in a monoid.
Oh.
So you take the product. So it's really nice the way as I said, it's just that it becomes so natural that it's easy to work with. Okay. All right. So I'm going to now stop thinking about Drinfeld. Yeah. You mean this? Yeah. Yeah. But this shows up all over the place. This kind of things. Yeah. Okay. Okay. But this, of course, this language of multi-segments only works in type A. It doesn't work in higher in other types. But it's still, I'm only talking about type A today. Okay. So then let's continue with the similarities between the two subjects. So there's a notion of standard modules in quantum affine algebras, where they're also known as while modules, and there's a notion of standard modules in the language of in the p-adic world. Yeah? So in both cases, they're universal modules, okay, with in some suitable way, and they have a unique irreducible quotient. Or sometimes they might have depending on what you do, it might have a simple circle. Okay? So in the case of quantum affine algebras, for instance, the standard module was defined by generators and relations, and you can show that it's actually a tensor product of fundamental modules taken in some very specific order. And in the case of p-adic groups, well, this is you remember I told you how to produce the irreducible module. It was by parabolic induction, and that's exactly what goes on. That's the standard module. There it appears as a circle. Okay. And these things were done. So Presley and I did some of this around 2000, and I think Lapid and Minguez, no, I might have got these names slightly wrong. Yeah, maybe did it around a similar time. Okay, so the subject was sort of developing more or less in parallel, and not, without knowing this to be the case. Okay, so we have this huge family of modules, and they're too big to study. So the standard way to progress in the subject is to look at special families, and you need some input coming from somewhere else as to what is the correct family to look for. And that input, for instance, came originally from the work of Kirillov and Reshetnikin, where they conjectured the existence of certain kinds of modules who had nice characters. And they're now called the Kirillov-Reshetikhin modules. And in the language of segments, the modules that they conjectured existed and had all these nice properties has its Drinfeld polynomial, let me continue to call it that, written in terms of segments corresponding to this element of the monoid. So what we're doing over here is we're starting with some fixed interval, and then you keep expanding the interval by 1, each endpoint by 1. Okay? And so what is the virtue of this? It means, so in the language of Drinfeld polynomials, what you're doing is that the difference is what gave you the index, and you're keeping the difference fixed, and you're increasing the sum by 2 at each step. Okay, so these are the Kirillov-Reshetikhin modules. And if you look at the p-adic literature, you'll see that the exact same modules were studied by Brigitte Spey in 1981, so a bit earlier, and they're in the context of discrete series representations. Okay? And they're known as Spey modules, and they've played an equally important role in the development of the theory of in the p-adic theory. Okay? So let's continue. So then there is this notion of snakes and ladders, which was introduced by Mukin and Young. They called it snakes in the quantum world, and Lapid, Minguez, and so on called it ladders in the p-adic world. In both cases, okay, so in both cases, these are modules associated with an ordered multi-segment, and you require that the endpoints keep increasing. Okay, so the Kirillov-Reshetikhin modules are a very special case of this. Okay? And so they studied these modules, they proved all kinds of interesting results, interesting for their theory. Sometimes they overlapped. So they have very nice character formulae and things like that. These modules, they have, all the weight spaces are one-dimensional, at least in the quantum world. And even then, even in 2014, nobody really realized that a snake module transferred to dualized to give you a ladder. Right, so it's also very curious that they have the same sort of name, but affine Schur-Weil duality transfer tells you that a snake module goes to a ladder module. Okay. So what brought on the connection? So why did people start to, why was the connection revived in some way? And that really came in through cluster algebras and the notion of monoidal categorification. Okay, so here's a quiver, all right? And this was introduced by Hernandez and Leclerc. And so if you want a cluster algebra, you need a seed. And the seed is given by Kirillov-Reshetikhin modules. Okay, so omega minus 1, 1 is omega minus 1, 0. So you can see that all these things are exactly Kirillov-Reshetikhin modules. So the segments, so if you look at this one, for instance, I think this point has not, oops. Oh, what did I do? Sorry. Oops. Oh, okay. Yeah. So if you look at this, for instance, the index is, so the segment, this is minus 1, 1, and if you decrease both endpoints by 1, then you get minus 2, 0. Over here, you decrease further, so you get minus 1, 3. So this quiver it's a huge infinite quiver, and it's labeled by the Kirillov-Reshetikhin modules, or if you like, the Spey module. Okay. And so they started with this quiver, and let's give this quiver a name. So the quiver is Q, and the initial seed of Kirillov-Reshetikhin modules is X. Okay, and then you start mutating, and as you mutate the quiver, what you find is, so obviously, if you look over here, we're not picking up all the Kirillov-Reshetikhin modules, even as you as you go further down the ladder, but as you mutate, you pick up all the Kirillov-Reshetikhin modules. So it's infinite. It just continues. So the number of elements in that in the Kirillov-Reshetikhin module. It keeps increasing. So, yeah. So as you mutate the quiver, what you get all the Kirillov-Reshetikhin modules. So this was one of the results that they proved. And Bing Duan, Jianrong Li, and so on also proved so that some of the snake modules appear as cluster variables. Okay? So more exactly, what did Hernandez and Leclerc prove? They showed that. So perhaps I should say so. So we have our category F, which is finite dimensional representations. And let's just say that they're indexed by these omega ij, where I and j are integers. Okay. And so there's a suitable subcategory. Actually, in this case, yeah, there's a suitable subcategory that you have to take. Let's just call it F naught for the moment. It's not important. And if you look at which is a monoidal tensor category as well. So you can talk about its growth and decaying. And so they prove that you have injective homomorphism to this cluster algebra. It's the other way, probably, to the cluster algebra, okay? Which took the initial seed to the Kirillov-Reshetikhin modules. But then once you have such a map, then you want to know, well, what is the image of a cluster variable? What is the image of the cluster monomial and things like that? You expect this to be good. So in general, it's not known that the image of a cluster variable is it's not known what kind of image a cluster variable has over here. You know, it's perhaps a representation, but you don't know exactly what its label is, for instance, and so on. So this map exists, but they conjectured that cluster. So their conjecture was that cluster variables map to irreducible representations. So I'll tell you what prime means in a minute. And that monomials, cluster monomials, map to irreducible tensor products of the corresponding cluster variables. Okay. But even if you prove this conjecture, you still wouldn't know what's showing up over here. You wouldn't know if all modules that live over there show up as images of cluster variables. You wouldn't know how to characterize what modules do actually show up, and so on. Okay, so there are a lot of open questions which lie in this. So the only case where a complete answer is known, for instance, I think, is in the category. So they also have a category C1. I won't go into it, but it's a very small category. It's associated with a finite quiver, and so in this case, you know, the correspondence is precise. In all the other cases, people take various finite slices of this quiver, and in those cases, but the quiver is still not a finite type, so they know this conjecture, but they still don't know what its image is. Okay, so that is the sort of question. Yeah. Okay. So, but then how do you begin to answer this question? How do you begin to answer the question? What property should the module have for it to be the image of a cluster variable? Right? I mean, cluster variables are very special, so the modules that you're picking up should somehow also be very special. And the question is, what are these modules? Right? How do you think about them? How do you look for them? So, so this is the question now that I want to discuss. What should I be? You know, where should I look for me to make a guess that it could be a cluster variable, and then somebody else who knows about cluster mutations could prove that it's a cluster variable. Right. So, so what are the properties that this conjecture tells you that a module should have? Okay. So cluster variables sort of are indivisible objects of your algebra, right? You can't write them as further products of anything. So that means the module should have a similar property, and that property is precisely the property of it being prime. And prime for half algebra just means you cannot write a module as a tensor product of two other modules in a non-trivial way. Okay. So we're looking for prime modules. Okay, and then what further property should it have? So if you take a cluster variable and you take any power of it, it's a cluster monomial, right? So since you want cluster monomials to go to irreducible modules, that tells you that you need the tensor square or any tensor power, right? So if the cluster variable x goes to a module M, then because of the ring homomorphism, x power r goes to m tensor r. Right. So if this is to be a cluster, so if this is to be the image of a cluster variable, then you really want this to be irreducible if you want that conjecture to be correct. Okay. So this is what, so this is something that you want. Okay? And these modules are called real. I think this goes back to Leclerc's definition. So a module which has, if m is irreducible and m tensor r is also irreducible for all r, then you say m is real. Okay, so in both subjects, people had studied these kinds of questions before. Okay, so let me again continue with a little bit of the history. But really, it's after Hernandez and Leclerc began noticing these conditions that people began to notice that also that there was this connection through Schur-Weyl duality. Okay. So why did this whole business come up? This is because, as I said, Leclerc introduces notion of real and imaginary modules. And so a module is imaginary if its tensor square is reducible. And it came up in the context of the work of Bernstein and Zelevinsky on the dual canonical basis. Okay, so I guess he gave an example. So I guess the point was that there's some element b in the canonical basis such that if you take its square, it's not in q times q power z times the canonical basis. So it was in that, and then Leclerc proved that in the case of Hecke algebras, pulled it back through Schur-Weyl duality, and he gave an example of imaginary modules in A5. And that was back in 2010. Yeah, 2006, 7, I forget. Okay, so this really goes back a while. And he gave a single example in AN. Okay, and since then, until 2018, no further examples were known at all about imaginary modules. Okay. So let's talk about, so before we continue about real modules, let's talk about prime representations. So of course you want examples, and then there are tons of examples in the literature, going back to the Kirillov-Reshetikhin modules, the snake modules of Mukhin and Young. And so once you introduce a notion of prime, then you want to know what all the prime objects are. This is a hopeless task. But in the case of quantum affine A1, this was proved 30 years ago, and it more or less stayed there. They're just the Kirillov-Reshetikhin modules. Okay, so the Kirillov-Reshetikhin modules in the case of SL2. So in SL2 hat, the Kirillov-Reshetikhin modules are just the n plus 1 dimensional, n is bad, r plus 1 dimensional representations, irreps of SL2. So they're sort of totally uninteresting in that case. So one has absolutely no idea of how to characterize prime. You have lots of examples, but there is no real understanding of what links them in some way. Okay? All these examples, however, they have this one thing in common: they're real. Okay, so then one might be tempted to say that prime modules are necessarily real, but Leclerc's example is prime and it's not real. Okay, so there are plenty of imaginary prime modules. Okay, quantum affine algebra, all modules are real. So this is one of the, I mean, usually you prove a result for SL2 and you think, yeah, it must work in higher rank. So it's very unusual for it to break down so completely as it does. And actually, no examples were even known in A3. So certainly till Leclerc came up with this example, everybody believed that all modules were real. It's just that we couldn't prove it. But so it's a total breakdown of things there. Okay. So what are these modules called? So what are real representations called in the p-adic literature? People studied it there as well. There they called it square irreducible, and it has a long history. Okay, so a module is called, they didn't call it real, they just asked the question, when is the tensor square of a module irreducible? So they called it square irreducible. So Minguez and Lapide, they gave a sufficient condition for a module to be real, square integrable, and it's a very combinatorial condition based on multi-segments. And you can use their examples, you can use their conditions to write down more examples of imaginary modules. but it's really not easy to do because the combinatorics is quite hard. So you can write down some examples, but you can't write down a family of examples, and you have to check every time that their conditions hold. Okay, so. And there's one thing about Schur-Weil duality, it's really not perfect because when you go from GLN to quantum affine algebras, the rank bumps up, okay, because there's a level rank condition over that. So although Lapid and Mingus, for instance, couldn't tell you at that point whether imaginary modules existed in A2 or A3. Okay, it was just not known. Okay, so yeah. So now I want to talk about some work with Brito. And so I've been interested in all these things for a long time. And so I'd like to know how to classify prime representations, or at least I'd like to know what families there are and how I develop some methods towards that. Okay. And I'm also interested in trying to find out what imaginary modules are, how to produce lots of imaginary modules in some canonical way that perhaps has a chance of generalizing. Okay, so both definitions are very nebulous. I mean, saying that a module is prime is not very helpful, and nor is saying that a module is real or that its tensor squared is irreducible. It doesn't really tell you how to approach the problem. This has been an issue. And when I say I want to give examples of imaginary modules, I want to tell you what the associated Drinfeld polynomials are, exact index. So we managed to do both these things in some way. And again, it came really from sort of understanding Kirillov-Reshetikhin modules and understanding their limitations and how to generalize them further. Okay, so let's go back and look at what the Kirillov-Reshetikhin modules were. So they're indexed by these intervals, multi-segments, ij, I plus 1, j plus 1, and I plus r, j plus r. So we just asked a very simple question. So this is an A1 phenomenon, right? This already happens in SL2. So now you're just lifting it to, you're changing the difference of the indices, right? J minus I, but you're keeping the increment the same. So we just asked, well, so why should we raise it only by 1? What if we raise it by a random set of integers? Okay. So for instance, you could raise the next one by 2, the next one by 6, and whatever you like. Okay. So these are actually what are called families of ladder representations. Again, the difference is constant, but the indices change. The sum changes. So if you're careless with this choice of increments, the module you get will not be prime. It will break up as a tensor product of prime modules. So what is the correct condition to impose so that this module stays prime? Yeah. So that condition is my interval overlapping condition. Okay. So every successive interval has to overlap. Okay. And that imposes a lot of restrictions in a very natural way. Okay, I'll just write on the side. So let's just look at an example. So for instance, if you're taking, so supposing it doesn't really matter. So supposing you're taking omega, I want to take 0, 2, omega, 1, 3, omega, and now I took omega 2, 6. Okay. So if you do the arithmetic, 2, 6 is not correct. So I want to take 4, 6. Okay. Now, if you do the interval, the overlapping condition, you'll see that these two overlap, and these two don't. Okay. The difference, and our point here is that the difference is always 2. Okay. So the restriction in the parameters is very strict. So you can't take random collections of numbers over that, and so it's actually a very rigid condition. And so this is what we call the higher rank Kirillov-Reshetikhin module. It takes into account further points of reducibility than the ones coming from SL2. That was the point of this. Okay. And as I said, these are ladder modules, a snake module, so we know that they're prime. In this case, you can give a simple proof. Thank you. So now we were able to prove a classification theorem. Okay. So So we take a so we take an element of my monoid, which I call P plus, okay, and we take any collection of elements. We take a product of elements of omega L1 M1 LR MR, and you require that the difference be constant. Okay, that the index is constant. Index of the Drinfeld polynomial is constant. Then the corresponding module can be uniquely written as a tensor product of generalized Kirillov-Reshetikhin modules. Okay. So this is this is very false if we work with just Kirillov-Reshetikhin modules, but so this result and its statement is exactly the old result that Presley and I proved in 1990 for SL2, that you can write any irreducible representation for SL2 as a tensor product. But now this, so this is an analog, but it's still very limited because it only proves it for when the differences are constant. We don't know how to do it in general. Ideally, you would want a result like this, where Li minus Mi varies. Okay?
So how do you know which like the end you're working with?
Yeah, so there I'm fudging a bit. But so some of these restrictions that I put are you work with n large enough. But if you're working with smaller n, then you have to put in about. Yeah. So, but that's
The indexing set is the same no matter what the end.
I'm sorry?
Is the indexing set the same no matter
Yeah.
what end you work with?
Yeah. No, that's not true because so for instance, if you're working, let me correct myself. So if you're working with A2, right, and you're looking at the second node, right, then the indexing set will only be so you'll only have 2 0 2 2 2 4 and so on. Okay, but if you're working with A3, then the indexing and the second node, then you'll have 2 0 2 4 2 4 2 2 6 2 10. You get more points of reducibility, but it stabilizes after that. You don't get anything new. So there is n large enough for which everything that I'm saying is correct. And I know how to modify it for smaller n. Yeah.
So in the SL2 case,
Yeah.
the Kirillov-Reshetikhin modules had an interpretation that with respect to SL2, those high rank Kirillov-Reshetikhin modules come from affinization of modules that were underlying SNF in some way.
Oh, you mean the Kirillov-Reshetikhin modules are so they're no,
So high rank is just
they're not evaluation modules, if that's your question.
or so they're not related to the finite dimensional representations in any way.
No, they are. Well, the representations are finite dimensional, and but if you're asking me, do I know what they look like as representations of SLN? That I don't know.
Okay.
So I don't know. They will be highly decomposable representations of SLN. Yeah. Yeah. So all these things have to be understood in high rank. Okay. Yeah. So, so as I said earlier, Duan and company proved that all modules are all snake modules. Did I lose my?
No.
Okay. All snake modules are come from cluster variables. Okay. So Kirillov-Reshetikhin modules are snake modules, so they're certainly the images of cluster variables. Okay. So how did we get to imaginary modules? Well, once you know a tensor product is sometimes reducible, you want to know what are the points of reducibility, and you want to know what is a Jordan-Holder series, right? So we decided to start looking at the tensor products of Kirillov-Reshetikhin modules and seeing if we can understand the Jordan-Holder series. Okay, so okay. And this is not known, even for Kirillov-Reshetikhin modules. For Kirillov-Reshetikhin modules, there's an old result that I proved where you do know the points of reducibility, but it doesn't mean that you know the decomposition. Yeah, well, maybe for AN you can do it, but in general, yeah. Okay, so we tried this. I would say that I didn't know it at all because, so let me explain. So this is how we got to imaginary modules. And so we took a very simple example. We're actually in A3, not A4. And we took the tensor product of two Kirillov-Reshetikhin modules. Okay. So so as he said, as you said, the Kirillov-Reshetikhin modules are just evaluation representations. So what we're looking at over there is V2 omega 2 tensor V2 omega 2 as SL4 modules. Okay. So it's very small. So you can write down his Jordan-Holder series very easily. Okay, so this is just, well, let me not try and do that. So so the Jordan-Holder series, when you work with it as A4 modules, it has three constituents, three Jordan-Holder constituents. And this choice of parameters that we've made, this choice segments that we've made, guarantee that this module is that V contains a copy of the trivial representation. Okay, so I know two of its constituents already. One is the top one, which is just the product of all four elements. One is the trivial. And then the last one we found was this one. Okay, so this is, and now if you look at this Drinfeld polynomial over here, it was exactly Leclerc's Drinfeld polynomial. Okay, so right, so this is so we just did this comparison with Leclerc's example, and we noticed that it was his example. And then we gave a different proof of his example. Okay, so which didn't go through quantum affine algebra, affine Heck algebras, but was lived in this world. And so this, I think I was in Bonn at that point, and Katerina kept talking to me about caps and cups. And so I think really I had this idea from talking to her about these things. Oops. So this module V, so let me just write. So this is a dual module like this. Okay. So I'm just calling it V1 and V1 star, the modules there. And then we took V star, and which perhaps looks like you have to flip the order. So it looks like V1 tensor V1 star, tensor V1, tensor star V1, something like this. And then you over here you have so you have a trivial here, but you also have a trivial here. So you can project down to V1 tensor V1 star, the module that you started with. Okay. So you have this duality. Each of these modules are dual. You take the further dual of the tensor product, and then suddenly you have this cup map, which takes you to the original module. Okay, and this module, so that's what we did here. And the module V that I have over there, well, that has as its irreducible head. We know what its irreducible head is. Okay, so we found that this was enough. So then you have to work a little more, and this was enough to prove that the module is imaginary. So you see, so this map. So I have this map from V star. So V star tensor V down to some irreducible module. Okay, omega 1, 3, etc. And then I restrict to my component, irreducible component M, and that has a non-zero projection onto that. And that's enough to prove that this module is reducible. Yeah, you need to know a little bit more about the way these things work, but decomposition works, but this essentially is enough to prove that the module is imaginary. Okay, so now once we had this proof.
You end up with 0, right?
I'm sorry, say that again.
The image of M tensor M. Where?
So you have M tensor M here.
Well, there's 3 maps, so
it ends up here.
Oh.
That's just subjective. Yeah, and M tensor M doesn't have the right Drinfeld polynomial, so it doesn't have the same Drinfeld polynomial as this, and that's what tells me that it's irreducible, that M becomes reducible. Okay. So once we saw this example, it was clear to us how to generate lots of examples. You just take, and the proof took a few months, but so the theorem can just be stated as the tensor product of generalized Kirillov-Reshetikhin module with its dual always contains an imaginary module. Okay, so and we can write down its Drinfeld polynomial explicitly of the thing. Okay. And these examples don't appear in the framework of Lapide and Minguez. And okay, so finally, I just want to go back and tell you what our example of what our method of proving that these modules are imaginary tells you about cluster algebras, which I apparently can't spell. Okay, so of course, everybody knows that cluster monomials do not span the cluster algebra. So what did we do? We took two irreducible modules and we tensored them. Both of these irreducible modules are cluster variables. We showed that you had an imaginary module, that means a module whose tensor square is reducible, appeared in its Jordan-Holder series, okay? So now if you're doing cluster theory, so we have this cluster variable x1 and x2, right? And you want to know if this can be written in the linear span of, so this is a product of two cluster variables. Is it in the span of cluster monomials? This corresponds to V1 tensor V2. And in this module, we showed that you had some, so you write its Jordan-Holder series. So let's call them U1 plus U2 plus U3. And this is imaginary. So whatever you do, this cannot come from a cluster variable or a cluster monomial because its tensor square is reducible. That means that x1, x2 just is not in the linear span of cluster monomials. So it's a completely trivial way of well, it's not trivial, it's a different way of producing concrete examples which show you that you cannot have that the cluster monomials don't span. Okay? They don't even span products of two cluster variables. Okay, and so with that, I think my time is up. So thank you very much.
Are there any questions? If you have a question, we'll pass the mic.
Do you have analogs of T-systems for these higher rank KR modules?
Well, Mukin and Young proved these extended T-systems, right?
Oh, it's in Mukin Young?
Mm-hmm.
Oh, okay. Okay, fine.
Yeah.
And I had a question. This conjecture of Hernandez-Leclerc you mentioned about the cluster variables being, can you just state it again? And is it still open, that conjecture?
I think parts of it are still open, yeah. So you have this map from the Grothendieck ring to, from the cluster algebra to the Grothendieck ring. The question is whether a cluster variable maps to an irreducible representation and cluster monomials to irreducible.
And sorry, is the question whether it's like whether every prime?
No, that's known to be false, I think.
Okay.
No, that's known to be false. But the image of this map is, yeah. So even if you believed that cluster variables went to prime representations, cluster monomials to irreducibles, you still wouldn't know. They don't have a conjecture as to what the image is.
But they all go to the conjectures. They go to prime real
variable. Yeah.
The variables.
Mm-hmm.
So in this classification, mutations.
Mm-hmm.
What mutations? Do they correspond to some functors on your mutation from different Cs? Do they correspond to functors in the category?
No, I don't know. I mean, in infinite type, I don't know. When you're working inside if you work inside a quiver of finite type, if you take a slice of this quiver, which is a finite type, then it just gives you the Jordan-Holder series, the mutation rules. But I don't know what happened. Yeah, I don't know how to see the mutation.
Any further questions? Yeah, let's thank you, Mr.